So hello everyone, and this Frits and I are both PhD candidates at Leiden University working with LOFAR processing, and my goal is mostly on the infrastructure side and the software development side, and Frits is mostly a scientist, but we both got pulled into this whirlpool of standardizing software installs. So we'll talk about our experience compiling software, building images, and testing those images, and why that's useful for us. But first of all, a bit of science. So this is what a galaxy looks like. In fact, there's a lot of galaxies in this picture. And they're made by LOFAR, which is a radio telescope. So it can work in the Netherlands even when it's cloudy and raining, which is great. But it's actually a European telescope, so it's based in the Netherlands, but we have antennas all around Europe, from Ireland to Estonia, or Latvia to Italy to Poland. And it's an aperture synthesis telescope, which means that all of our imaging actually is done in software. So all of our combination of data needs to be processed a lot more than other telescopes typically do. And that's why we need high throughput computing and high performance computing. And we have multiple science cases that one observation can serve. And this is a big list of all of our key science projects. And you can see that it spans from solar science, so that's in our solar system, up to epoch of reionization, which is basically fancy speak for the first stars in the galaxy, in the universe. So from the nearest to the furthest away cosmic phenomena we can study with LOFAR. And that's both good and bad, because that also means that our data sets need to be very general, which also makes them fairly big. And it needs to be processed by many different software suites. So one of the science cases that we're focusing on is the Survey's key science project. So Surveys is basically the idea of, can we make images of the entire northern sky at resolutions that we've never seen before, at frequencies we've never really seen before, and at sensitivities, so faintness, basically, that we've never reached before. And basically that leads to 40 petabytes or more of data that need to be processed, reduced, and then we make images like these little guys here that if you get bored, you can see. Every slide has a new little surprise. And we actually have hundreds of thousands to millions of these images that we need to classify. That's another thing. So there is even a machine learning domain of so first of all, how do you make these images, these little galaxies, and then how do you classify them, and then what science do you do with them? But the first important part is you have to make these images, and they have to be of a specific quality. And we do that with this software. It's a very simplified idea. First, we have a calibrator somewhere on the sky, and then we use the results of that calibrator to determine basically voltages on our antennas. And once those voltages are determined, it's basically like a least squared fitting, more or less, to determine using a model of the calibrator, so we know what it looks like. And the radio sky doesn't change very much, at least in some places. So using those solutions, we apply them to the science target, which is the 8-hour observation that we have never seen before. Or actually, we've seen it with other telescopes, so that actually helps a lot. What we do is we take another telescope's solutions, and then we use those solutions to bootstrap our image or our calibration solutions. And then finally, we do the imaging where we try to find as many faint sources as we can. We'll go as faint as we can and create a scientific image, which hopefully our scientists can do science with, like Frits here. So some of the goals of our software distribution is take those pipelines that we just shown, make them give correct results, integrate them with our processing software, or rather integrate the software with our scripts, because we have a lot of scientists who write a bunch of scripts, and they don't always run or do the right thing. Give some kind of versioning information, which leads into reproducibility. So we say, this is the version that works with this script, and it gives this kind of data. And then that will, with images or with containers, that will allow people in Italy to do the same data processing and get the same results to confirm that the science we did is the same or is accurate. So next we'll have Frits talk about containers and images and how we build them.
Yeah, so I'm mainly responsible for delivering these images to our community. And this basically all started once we needed to update the LOFA software on our own computers in Leiden. And then we figured out that the LOFA software is very near the bottom of this XKCD comic, that as soon as you need to change a little bit in your setup or in your configuration, then everything goes to hell and it becomes a real pain to install. So that's why we came with the idea to start using containers for the LOFA software, because then everything would be delivered in one nice single package. So one of the main reasons that the previous speaker also already mentioned, we have this increasing dependency hell. So the LOFA software has its own number of dependencies, then there are tons of Python packages that are required, and it just keeps growing and growing with every new pipeline that we add. So if you can package that all together and save the users from having to install all those dependencies themselves, that would be great. So that makes for a very easy distribution and for a relatively hassle-free setup on the user end. And finally, the sysadmins really like that there's only really one system requirement on their end, which is either, well, in our case, singularity. And it can also save you when the sysadmin decides to update the system and accidentally break the entire Python installation for the whole university, for example. But our containers were still working because everything was neatly packaged inside. Now, why we chose for singularity is basically because Docker requires sudo writes, as is mentioned multiple times here already. So singularity was the immediate choice for us because it doesn't require any sudo writes, and it basically runs as the user itself. Once you enter the shell, it's basically as if you're running from your own computer. And finally, it was also tailored already for HPC, although we're actually technically high throughput computing, but this still applies to us. So the way that I have set up our distribution, I stack containers on top of each other, just like these pans are stacked on top of each other. And I did that because I wanted to try and separate the relatively slow-moving dependencies, which are just the libraries that hardly ever change, from the very fast-moving front end, which is the LOFA software, which basically changes every day. So by using multiple containers which each target these separate things, this gets a bit easier to set up, and it gets a lot faster to update because we don't have to rebuild the entire OS dependencies and then the software. We just rebuild our software image, for example. So the way I do that is that we start actually from a Docker image, which is CentOS in our case, because that's very close to the host systems that we are running on. Then I built in this image, which I call the base image, I built all the standard library dependencies, which are not LOFAR or astronomy specific. Then I have another LOFAR image, which builds all the standard LOFAR processing software in there. And then finally, we have some exotic images where you can put in your own custom or proprietary imaging software, for example, that you want in there. So this is actually a sort of three-stage build process that we go into. And this is all relatively automated because I built my images on the Singularity Hub. And this is linked to my GitHub repository, and as soon as I push a commit to one of the recipes, then Singularity Hub triggers a build on that recipe, and then in 2 hours or something, you have a new container ready to go. And then the user can just do Singularity pull something, and they have the new container ready to go. And this is actually part also what drove my separation of these containers, because it's a free service, but it has a 2-hour build limit. So if you try to build everything in one go, you will grossly exceed that 2-hour limit. So now actually this is all broken up in nicely sub 2-hour chunks of building. And yeah, and so these images then are used for either processing our data locally now, or what Alex will tell us more about, to integrate into workflows and our own continuous integration.
So yeah, so what we first did is we built some containers and we tested whether they worked with one of our pipelines. So how do we do that? We just logged into a worker node or to a head node, and then we ran it on a test data set. That's great, but you can't do that every day because that's not what your PhD is about. Otherwise, well, it's not very fulfilling, honestly, to run the same thing every day, which is what continuous integration is for, actually. So why don't we do that? Well, we can, so running, we're very heavily coupled with the LTA. So all our data, our petabytes of data is at the LTA, which is conveniently at Surf Sara. And conveniently as well, we're running pipelines in production where every day we create an image, for example. So what I decided to do is, why don't we use the exact same workflow engine that we're using in production, that runs all of our processing on the grid nodes here at Surf Sara on the Gina cluster. Why don't we do that and then run it every day and have a continuous integration pipeline running in the exact same environment as our processing? So basically, it does the same thing. It downloads a container, and then it processes all our data. And then after that, we can just, since the workflow engine is called Apache Airflow, it's a general Python workflow, we can add steps. After that, you add a step that basically creates a version number for that container or that image, and it puts it up somewhere. And in fact, that's what we did. And this is what the CI workflow looks like on a high level. So we check whether there's new versions of our scripts on GitHub or of our Singularity container. And then the pipeline that you saw previously basically is here. It stages some data, so it puts some data online, and it processes the calibrator, processes the target, so the science target. It creates some diagnostic plots, something that we don't have yet, but it's very important. We need to create quality criteria for our data because we know that our data has been processed, or actually we hope that our data has been processed. But once it's processed, we save it somewhere, but we only have some base heuristics on what our data should look like. So again, with a generalized workflow, you can put that in and then update it over time. And then whenever something fails, you could even, since you have GitHub integration, you could just open a GitHub issue or email the person who broke whatever the thing that got broken. And another thing we can do in Dark is the things we haven't really done yet, but we are working on, is create an image and then upload that image. And since it's the exact same data set processed every time, you can see how our scientific image changes, which is a great first-order heuristic on whether something really breaks, or something kind of breaks, or something probably doesn't break. And what we're doing manually currently is creating a nightly release where our software and our Git repositories are uploaded somewhere, but eventually we'll create some versioning scheme. And this is basically what it looks like. So this is just a very long linear workflow of everything being staged, processed, and then when something fails, you can schedule it to send an email, basically, to either the CI developer or to the GitHub developer, or the scripts developer. And this is arbitrary. Like this can be, what you can do is you can actually add extra repositories, so you can test multiple different science cases. And that's something that we plan on doing. Is instead of just this one science case where it makes an image, here you could also branch off multiple different science cases, and then with one push, you can test every single science case that is served by that container. So your users can be happy, or at least content, that A, the software works, and B, that it produces some meaningful images or data. So with that in mind, I think we can wrap up. Yes.
Just to keep it exact.
Yeah,
I have my pointer. Yeah.
Yes.
So yeah, basically the main reason that we started using containers is, as their name implies, they contain all the software that you need. And for us to spawn the buzzword again, to produce reproducible results. So for us, we can now just give someone an image, and everyone that we give that image to, we will get the same result. But it's also very important for us, as Alex mentions, if something kind of breaks, we aren't the best at versioning sometimes in astronomy, so we don't have a version 1.0 or version 1.2. It's basically just, oh yeah, it's commit number something something. So it becomes really hard to check what software people have actually used. You should just say, oh yeah, I use this software. That commit can be anywhere from a few days to a few months old. So by having these images, we can trace also exactly what has been installed, because you cannot change the image anymore after it's been installed. So it's very reproducible in terms of either science images, results, or non-results, such as crashes or bugs. And the future work that we were planning to do is we want to tend this to the multiple science cases that there are. Right now it's very specific to our science case with the surveys and just bulk data processing, but we want to eventually generalize this to the whole LOFAR community so that they all can get a single image which all tends to their needs. And for that we need to ensure that, first of all, they serve multiple science cases, which means at some point we will need to query with the user, like what software do you need, how does it need to be set up, etc. And it also means that we need to find out somehow how to check the quality of our results that the images will produce, because in astronomy it's usually not a clear-cut case like something's wrong or something's right, because it can be, for example, that you lose a little bit more data because your pipelines think it's bad data, but it's actually a good thing because it's getting rid of that bad data that you weren't getting rid of before. So it can be that some things changes which at first glance seem like things are going wrong because you're losing more data, but they're actually going right because you're removing the data that should be removed. So we need to think about how to implement the data quality criterion, and we need to start implementing tests, like Alex said, that we just run every time there's a new version of the software, we run it and then we compare it to previous results. Which brings us to unit tests and versioning. As I mentioned before, it's very important that we have a version that we can reference, like this is what we used. And that's also why we need to start implementing these tests. And these are all things that we need to decide on. We need to write the tests themselves. We need to decide on some sort of versioning scheme. We need to somehow figure out how we can make these images persistent, like that we have them always available for people to download, even when it's maybe 2 years down the line, I guess. And finally, we will need to integrate a little bit more on our own CI, because we don't run this on a publicly thing like Travis or whatever because of the data and other things that we're dealing with. So we also need to see how we link this into our GitHub, that as soon as something changes that we can react to that. And with those points, I will leave you at our thank you slides, which of course mentions a few important people from both Surf-Zara here, which provides us with your infrastructure, and the University of Leiden, where all this work is being done. And well, you can find us at those 2 email addresses if you want. Thank you for your attention.